I need to move the lecture along a little bit. I realized there was something I could spend a little bit more time with that is part of two-dimensional motion. They probably handled it in that chapter 3, actually, but it's relative velocity. And we're going to look at that right now and knock that out and then move on to some other things. So relative velocity in 1 and 2 dimensions. In 1 dimension, it's just pretty simple. Actually, in 2 dimensions as well, but we just need to classify it as a concept, and so that you got to handle the things. And it's the situation where, like say you're out on the beach, right, and you see a bird flying. So this will be one-dimensional relative velocity. You're out on the beach and you see a bird flying in the air, and they're just staying in one position, or they might even be moving backwards. So they're pointed forward, and they're kind of flying back. We've all seen that kind of thing. Well, the speed relative to the ground, if you assume that forward is the positive direction, they actually have a negative velocity. How is that? It's because if you assume that the bird has a natural speed, like if there were no wind and the bird were flying along, they would have a certain velocity. And you call that the ground speed, okay? But then if you then say the ground speed and the air speed would be the same thing in that case because the air is not moving. But let's say that we have the air moving at a constant velocity as well, and let's say it's a headwind, so directly into the bird. Well, velocity is just a superposition. It's a vector quantity, so you add you add the vectors. Now, you remember you can only add vectors directly when they are on the same, along the same coordinate direction. So for a headwind, whatever you're calling that direction, and if you assume that the direction the bird is moving is positive, then the headwind is always going to be in the negative direction. But because velocities are vectors, one direction is negative of the other. So, for example, if you have a bird, so we'll call this one-dimensional relative velocity. So if you have a bird flying along the right at 2 meters per second, VB, and you have a headwind of I call this the velocity of the air or the velocity of the wind. I don't know. Wind. That's going to be whatever coordinate direction we call it. So we'll take the magnitudes, right? This will be the speeds. Well, let's do velocities. I don't know. And we can give it a direction just based on geography. Let's do that. Let's do, north, south, east, and west. So basically, the bird is flying due east at, I didn't give it anything. So VB, let's make it 2 meters per second. I don't know. It's pretty fast. 2.0 meters per second. And the velocity of the wind, the magnitude of it is 3 meters per second. And its direction is due west. Well, what is going to be the vector, the bird's net speed, his resultant speed, I guess we could say. The resultant velocity. Well, we didn't assign specific directions in terms of X, Y, and Z. But, if we set up the axis so that um, the directions corresponded to the X and Y axes, that we call east positive X and north positive Y, then we can say that in terms of the vector representation, the bird would be flying in the negative X direction. Sorry, the wind is blowing in the negative X direction, the bird is positive X direction. So if we were to write this out pictorially, in fact, the equation for net velocity, it's a little bit confusing. It's just a vector equation. It's just going to be this. So V net is equal to V, in this case, the V of the velocity of the bird plus the velocity of of the wind. In the West, our convention here is that when we're writing as a vector, so basically this is the equation for relative velocity. When you look at the concept relative velocity, they're just going to say this, right? For two different velocities, it's just the net velocity is the vector sum of each. Yeah. So, but when I practically set it up, when I relax the vector notation, then that's when I generally put in most books do, the sign relative to one another. Now, keep in mind, you can't even add these things if they're not on the same direction. You have to first break down, just like we've been doing with vector analysis. What is vector analysis? You break each vector down for its coordinate directions, and then you can only add those components along each coordinate direction that's the same. Then you put back find the resultant with the Pythagorean theorem, and then the angle with the tangent. Now, I've already reviewed that, so I'm not going to review those processes for vector analysis, but that's what it is. We were doing it with force mostly, but vectors are vectors, so you add them the same way if they're not along the same direction. We'll do a couple of examples when we get to two-dimensional motion. But for one-dimensional motion, it's almost trivial because they're along the same coordinate direction, so one direction is just minus the other. And so in this case, we would have the net, when we make it speed, well, we could say direction. The net direction is going to be net velocity is going to be VB I minus VW I, which is 2.0 meters per second I minus 3.0 meters per second I. So the net velocity is 1.0 meters per second, negative actually, 1.0 meters per second I. And that would be in the negative I direction or due west. So the resultant, basically, I'll say VBR, meaning the resultant velocity of the bird is -1, basically 1 meter per second due west. That's it. That's relative velocity. Now in two dimensions, we have to do just the in high school when you did this kind of stuff, it was like it was, you called it the parallelogram method and triangular method uh, of adding vectors, in this case velocity. So let's give the wind let's give the bird a crosswind, and let's make it go due not due but at an angle in the either so south of west or north of east. northeast, north, no, I don't know, southwest. That southwest is definitely a thing. So southwest, south of west is that way with this. Let's make it 45 degrees just to make it simple. So two-dimensional, the equation is the same, right? The general definition of equation for relative velocity is the same, but now they would be in different directions. So you would have to break it up into the components. So that's where it doesn't change really in terms of the definition. And just now, so in this case, a bird flying due east at um, what did I say, 2.0 meters per second. Enters an area of a constant crosswind, blowing at 45 degrees southwest at 3.0 meters per second. So again, it's still V wind is still 3 and VB is still 2. So if we were to set this up vectorially, a little bit different. Now, in this case, the bird's looking forward, flying backwards, this guy right here. So what about this situation? Well, again, it's vector analysis. So the resultant velocity of the bird is the vector sum of the ground speed of the bird versus the speed of the wind, which is different than airspeed. Airspeed refers to the speed of the object in the air. By the way, why don't we clarify that? The ground speed of the bird here, the ground speed of the bird is minus 1 meter per second. So if you look up, what you're looking at as a superposition of the bird and let's turn this way. So the bird's flying backwards because the superposition of his, what you would call ground speed, and the ground speed, well, if there were no wind, his ground speed would just be 2 meters per second. So that's really what that is. But then when the airspeed is in there, they combine and the bird flies back, right? But relative to the wind, to the air, how fast is the bird flying? And remember, it's the same thing that with those boats there, we were talking about in some stuff the other day, when they're in opposite directions, but relative to one another, it's kind of like you have the axis on one or the other. So like, if the bird doesn't even see anything but the wind, like for him, the wind is stationary. That's one way to think about it. So if the wind is stationary, how fast is he moving relative to the wind? Well, anybody want to take a stab before I tell you? What's the air? If the ground speed of the bird in this case is minus 1 meter per second due east, well, the speed is 1 meter per second and direction is due east. What would be the speed of the bird relative to the air? What is the airspeed of the bird in this scenario?
5 meters
Kimberly.
per second.
Yeah, hi. Yeah, 5 meters per, not 5 meters per second. So that's the difference in ground speed and airspeed. 5 meters per second, and it would be due east, the direction. Well, the velocity then would be due east. So the velocity would be 5 meters per second due east relative to the wind, or the speed is just 5 meters per second. So that's the difference. Now here, we can't just add them straight up, as I said, because they're not, along the same direction. So we have to find the coordinate components of each of these quantities. The bird then, let's say that's 2, VB equals 2.0 meters per second. And the wind is 45 degrees I'll try to stay a little bit consistent with the convention and make that vector a little bit longer. So maybe something like that. Okay. VW equals 3.0 meters per second. And I do have an angle, it's 45 degrees. Now, sine and cosine of 45 degrees is the same. It's square root of 2 over 2, which is like 0.707 something. How did I lose a marker? I need another marker. I don't know where it is. All right, so I got to find the components then. And so the components of VW, I'm going to have a component in the X and Y directions, which would look like the following. That guy is VW, and sine of 45 degrees. Okay. The theta is equal to 45. And this component VW times the cosine of 45. So the resultant velocity, now with the parallelogram method, actually you can kind of gauge it, right? The parallelogram method or triangular, you basically make a parallelogram. So I project this guy back over here. In high school, you actually do a graphical representation where you draw everything to scale, and you can pick the answer off from measuring the result, the diagonal. I don't know how many people did that. I think I started doing something like this back in, I don't know where, but we did that kind of stuff. And then this guy projects down, right? It has direction. So this would represent this vector here. The diagonal of that parallelogram would actually represent the direction. And the length would represent the, if you did it to scale, I just measure the angle. And technically, we measure from the positive x-axis. Anyway, it'd be this guy or negative whatever, negative that guy, and the magnitude would be the length. In our case, we can use an analytical method to figure that out. But it does make sense. What that's suggesting there is that if there's a crosswind, like the bird is flying this way, and the crosswind is like that, that's when you see the birds flying sideways, right? They're going like this, but then the wind is pushing them. So the bird will probably be doing, and he's not quite going backward because he hasn't flipped this 270-degree angle there. So he's flying, be something like that, right? Trying to fly forward and then going to the side. How many people have seen that see the seagulls doing that kind of thing down the ocean or on the sea on a windy day or something like that? Anybody know what I'm talking about? Yeah. But that's what it is. This is just this. That's what it is. That's how you explain it physically. So yeah, so the arc, the resultant in the arc in the extra, I'm just going to write the resultant as R, not V sub R. So Rx is going to be, the VB minus the VW, cosine of 45. And the RY is just the VW sine of 45. We'll calculate those in a minute. And the R is just going to be the Rx squared plus Ry squared to the 1/2. And the reference angle, now be careful, it's just when you use this tangent formula, it's always going to be the angle relative to the x-axis in that quadrant. So I'm going to call it R theta, just to distinguish it a little bit. Theta R, Theta R for theta of the resultant is actually that angle. And so when I do this inverse tangent, theta r, it's going to be of ry, the absolute value, and rx. So when I get that, it gives me the reference angle. Now, in this case, you can just say, we're going to convert it back to the north-southeast thing. So this would be, the headwind is southeast, but the bird is actually flying. Sorry, I said no. The wind is blowing southwest, but the bird would actually be flying southeast, so south of east. So whatever angle that turns out to be, whatever number of degrees southeast is how you would characterize the direction of the bird. Whew, so let's calculate the numbers and see if we get the same thing. So 45, that's a cosine, 0.70711 times VW, which is 3. And then yeah, so store that in that register. I'm not adding it. So 45 cosine 3 that's minus. Actually, I might have drawn that wrong. It might still be going backwards. This is what tells you that. Yeah, I might have drawn that wrong. Because here I'm getting that this quantity here is negative, which means that this term is larger than that term, which means that it actually still is going backwards a little bit. Yeah. So that's yeah. Well, that's actually pretty good. I mean, that I kind of made the error and then showed that why the analytical is so much more accurate, right? It's kind of probably right on the edge there. I'll show you what I mean. But let's go ahead and put it in. So VB was 2, right? Yeah. So 2 plus. Yeah. Yeah. It's like that. This isn't quite right. I should have made this vector a little bit longer. In fact, you might even see it because I wasn't careful. So it's got to be. So if that's 4, then this should have been 6, and it's not quite 6, is it? It is 6. I don't know. Whatever. Maybe I'm just not doing it. There's some other error in there somewhere. But the point is that Rx, I'm getting a minus 0.12. It's really small, the fraction point. Rx equals minus 0.12 and some change, right? You keep that in there. Now, again, I've stored this in my register, so I haven't truncated it at all, so it won't be any round off error. And Ry was just the 2.1 something, so 45 sine, and then 3 times, yeah, the 2.12, 13. So Ry is equal to positive 2.1213. Well, actually, I messed up. It might be negative because it's going in the negative direction. So that's negative. And that's why that's negative. So be careful about that. When I'm doing this, I get my sign. Because I use 45 instead of using 45 plus 100. Was that 135? 1 was 40 plus 80. 135, yeah. If I had used the cosine of the sine of 145, then I would have gotten the negative sign. And you can test that for yourself. 135, I mean. So yeah, 135. Wait, what? I didn't. Why not? So 45 plus, sorry, 180. It's not 135. It's plus 80 plus 180. So it's, yeah, sorry about that. So it's 225. Sorry, this angle is 225. Um, yeah, 135 would have just been here, 40 press. So that would be positive for y, because what I bring up. But 225 you would get, which is what that angle technically is relative to the, if you don't use the reference, it kicks out the negative sign. So the sine of 225 is going to be negative. Yeah, negative 0.77. But like I said, I like to use the reference angles because I like to visually see the right triangle. I can see it in there. So when I do that, I'm always dealing with magnitude. So I would have to manually put in my negative sign there because I'm not using the actual correct angle, which is 225. All right. So both are negative, and that's true. That's telling me that I'm going to redraw this picture because that's actually telling me that since both of the components are negative, my resultant is actually in this quadrant. So one way I could actually fix that probably is like this. Just make this a little bit longer. And this is just a sketch, right? I just want the sketch to be right, not throw you off. I've exaggerated it, but actually it would have been about right there. I think I've calculated what the proportion should be. That is a little bit longer than the one before. Now here, taking that down to 10, cross. Yeah, so you can see it's definitely in there. Yeah. I was a little off. So the angle should be close to 270 when you do it. So what I actually did here, just so it would graphically work out, just in case I kind of lost you because I was mumbling, is I went ahead and made it to scale to show that it should work out. I made this vector a third longer than that vector. And so now when I actually do the parallelogram method, it's going to work out to be about what the analytical method is suggesting, which is that the angle should be just as I can see it from here because this number is so small, it's less than 1, right? Like 1/10. So here, when I then project this guy over, sure enough, we're right inside the fourth quadrant whenever we draw our result. Sorry, right inside the third quadrant. So the angle is going to be a little bit less than 270. Like that. That's the result. So it's still going backwards. So to correct my demonstration, flying as opposed to doing like this, it's actually kind of going kind of at an angle, but slightly back. And we've all seen that as well, right? Slightly back along that direction. Always so cool. It tripped me out when I was a kid, seeing that. And for the first time. Many people remember seeing the beach for the first time. Oh my God, it was magnificent. I was I'm from South Carolina and grew up on the East Coast, so the Atlantic is very different than the Pacific. I can tell you that. First of all, y'all speak well. Y'all, I guess I've been here for a while. The Pacific Ocean is freezing. The Atlantic is warm. particularly where I am down in South Carolina. During the July, August. Oh my gosh, it's like so nice. On a nice hot day, the water's warm. I wasn't used to that when I came out here. I didn't even know, like, you would think. I know it's coming from from Alaska. There's some undercurrent. I forgot what it's called that runs down and cools the Pacific. But I mean, you would think, man, that it would be that's a long way away, but it's really cold and it's a lot of water. So I guess that's science, right? Sometimes things are counterintuitive. For me, that was a big one. Um, so let's finish this out. Let's get the magnitude, and then let's just do these two guys. Get the magnitude and the direction. So the magnitude, I don't think I stored that RY. Let me store it. No, I lost it, so I have to calculate it again. Where is it? It's just this. So 45 sine and 3. Yeah, 2 So store 1. Okay, so recall that guy. Mhm. Okay. Yeah, so it's not much different. The magnitude is going to be about the same as the y-axis that takes precedent. Whereas this was 2.12. I think I did do 3 significant digits initially. I did over here, but not here. Let's just go with 3. You can see there's a little bit of a difference. So with R, I'm going to get a value of R resultant. The magnitude is 2.12. 2.1. Actually, it's still 2.12, but it's well. Actually, it does round. I'll round. It's approximate. It's well, it is 2.21 technically the way you round it, but you can see there's a little bit of a difference. 2.124.7 as opposed to 2.13. But still, the total magnitude of the velocity I just reported up here rounds to for this bird, the magnitude of the total speed is 2.12 meters per second. And the reference angle for that bird is going to be, again, that was just the Pythagorean theorem, putting these guys in here. Now, putting the magnitudes of those things in here, that's going to be tangent, inverse tangent, that is, of 2.1213 over 0.1213, whatever. And you get a pretty steep angle. It's like 87 degrees, 86.7 degrees. So theta R equals 86.7. And this is 90 degrees, so I'm really close to that. It's pretty much what I drew, degrees. But the overall angle then is going to be 86.7 plus 180. So I distinguish between that by using theta R as reference angle. That's what it's called, this guy. So it would be this guy. And we got a little bit for the break. Yeah. And so, sorry about that. I'm not gonna answer that right now. Uh, this angle is going to be 180 plus 86. So, so the total angle then would be 26, 2667, 262, 66.7, 180, 86.7. Yeah, 266.7, 266.7 degrees, approximately 267 degrees. And that's what this whole thing would be. I guess you would say, translating in the terms of north, south, east, and west, you would say his velocity would be 2.12 meters per second southwest, southwest. Yeah. So that that's relative velocity. That's relative velocity. Yeah. So that's pretty much all of the concept, the physics concepts that are incorporated within chapters 1 and 4, and through 4, and got some classic favorite ones here: 1 and 2 dimensional motion. Yeah, look at the book here. Let's see. As I suggested it, let me help you out with that a little bit. Let's go back to let's let's go here for a second. Okay, something that makes me dizzy. Hmm. Yeah. See problem number 61 here? I think the dots represent the difficulty level of the problems. So let's take a look at that one. Take a look at that. um, now, let's demonstrate the problem. Let's go through the technique. We read the problem. Let's demonstrate it. What is it trying to say? But the first thing, you see down here where it says the motion is identical? You guys can even tell right here. A steel ball is dropped from a building's roof and passes a window, taking 0.125 seconds to fall from the top to the bottom of the window, a distance of 1.20 meters. It then falls to the sidewalk and bounces back past the window, moving from the bottom to the top in 0.125 seconds. Right there, I know that it's an ideal case because it's implying that the impulse force that the ball makes when it comes in contact with the ground basically is negligible and doesn't do any work on the ball or take any energy out of it. Well, I won't say it's negligible, but that it doesn't do any work. That's an ideal situation. It wouldn't have the same energy, but as you know this, you know this as well as I do. Um, otherwise you could make perpetual engine machines, right? It's not going to bounce up at the same height, which means that at the same position, it wouldn't have the same speed. And it would have to have that in order to go past do the same distance at the same height with the same speed. So right there, it's an ideal situation, even if they didn't tell you a few phrases later. But yet they do tell you a few phrases later. They say, assume that the upward flight is an exact reverse of the fall. Well, they basically implied that with that sentence. So that's implicit information. So just by reading, you start to gather both explicit and implicit information, right? The time the ball spins below the bottom of the window is 2.0 seconds. So that's how much it took the ball to go from the window down. How tall is the building? So right from there, I can see that because it didn't tell you like whether the ball could have fallen. They could have dropped it right at the top of the window. They don't say that. But when they come down here and say how tall is the building, well, I think um, oh, it does say that, yeah, because otherwise I could say, well, you don't have none. You could assume that, but it does say, it says a steel ball is dropped from a building's roof and passes a window. So that implies that there was some distance y above the window that we don't know what that is. But and yeah, so already I'm kind of formulating the sketch in my mind, the diagram. We've got the explicit information implicit. Let's go ahead and write that first. Again, remember I'm following the PPST. So explicit information, I might break this up into three categories of information. The information, before the ball gets to the top of the window, the information in the window, and the information from the window down to the ground. Just in my mind, that's just how it's organizing itself, the information. Um, Now, I don't know how I'm going to do the problem yet. I haven't gotten there yet. I'm just thinking about, just kind of percolating. This is how I do it. I'm showing you, trying to model the technique, right? Because this kind of thing alleviates from panic. What equation do I use? Oh, I don't know the equation. Oh, what I do. That kind of thinking is just anathema to me. And it's the kind of thinking that I did, but, when I didn't have technique, but, whatever. So that's how I'm thinking about this right now. And I guess I'll just, you don't have to like, I'm kind of doing it organically. So I'm thinking about the picture as I'm thinking about the information. So I'm going to go ahead and start kind of drawing the sketch even as before I specifically write down all the information. So, and I guess the diagram as well. So I'm going to put my axis on the ground so we can rest assured that and so the edge of the building is going to be my axis. So my building might be like something like here. I don't know. Put the image upside down. So here's my building. This is the roof. So maybe this is the window here. I don't know. And I've exaggerated it, right? Got really big windows. Um, so roof. And Y and X. This, I guess, is my delta Y in the region of the window. I'll call it that. That's the distance. I think they gave that distance, didn't they? If they didn't, they gave enough information to figure it out. But yeah, they don't give any of the distances. But in the other two portions, they give enough information to figure it out. So, but I'm just going to kind of delineate there. That's the position. And then this distance here is below the window. So you know, I need to have kind of names for these. So I'm going to call this Y of the roof. I want to, so it doesn't kind of mess up my picture here. Project back over here. So this position is Y of R for Y of roof. This position is Y top. This position is Y bottom. I'm gonna call this position Y ground or Y. I'll just call it Y naught, meaning not at time t equals 0, but at I'll call it Y ground because technically Y naught, I guess, would be the roof. But whatever, we can call it whatever you want. Now, also over here on the other side, I'm gonna do something else here too. I'm gonna say this. We know that some delta t's. So this delta t is 0.125 seconds, right? Yeah. So you know, and you could just say t is equal to 0.125 seconds. And then this delta t is 2 seconds. T is equal to 2.00 seconds. Now I don't know this delta t, this t here for that portion. But this is how I'm seeing it lay out. Again, in the end, you want to have all the knowns and unknowns of what you know and don't know. And however you organize it, it's all good. Right? So this t, I don't know. So I don't know any of the distance, the delta y's, and I don't know that time. Well, let's just write down now what I do know. I've kind of written it there, but I guess, yeah, it's actually there. Implicit information is no energy loss. So motion up, same as motion down. So ideal collision at the boundary, ideal bounce or whatever, however you want to say that to yourself, bounce, which leads to no energy loss, which implies motion up equals motion down. Okay. So that assures me that if I drop it from this position, the ball, it just goes down, the initial velocity is 0, right? Bounces down and then comes back up and hits that same position. Right? Going down is up. And I don't even I would say initial velocity 0. And then, and I might do, just to break it into two parts, maybe this is down and this is up. And just, I don't really need that, I think, but you know, the ball is falling down at that point, and then it bounces and then goes back up, you know, whatever. I don't know. So that's what I would say steps 1 through 4 would look like for me for this thing. Now, of course, now the concepts get you back here. I think I have all the information. I'm going to get this back. Okay, concepts. What concept applies? We don't have that many. General motion X, general motion Y, free fall, parabolic, centripetal motion, and then the other concepts, graph under a curve, relative velocity. Those is the only thing we've studied, right? So it's very easy to determine which concept applies to this. This is free fall motion, right? So it's only one object, and that object is going to explode. You could break it up into 2 different paths or not, or whatever. Point is, if you do that, then you'll have 8 equations, path down, path up. But I don't think we're going to need that. I think we'll just, because basically the path up is the same as the path down. So we'll just double the answers we get, right? In the end, for if we want to get the total. So again, but that's an analysis, right? I'm looking at that, right? I'm looking at, okay, that's again, that's part of my process. And you know, I know some of you've already doing that. You have a process. You're doing some versions of things that people I've talked to on your own. But I'm just showing you, trying to mimic how I would, approach something. So I'm going to have 4 equations. The 4 equations associated with free fall motion. Step 5 says just write the thing so you don't forget that's what you're doing. And I'm just going to write the generalized equations. In this case, because I have one option, I think the generalized equations are going to be the same as the specific equations, but we just write them in. So I've got velocity in the y direction equals initial velocity in the y direction minus gt. Then I've got y equals y naught plus v y naught t minus 1/2 g squared. Then of course g y squared equals v y naught squared minus 2g y minus y naught. And then finally y minus y naught equals 1/2 v y naught plus v y times t. Okay, it actually occurs to me that even though I have one object, I could technically say that I have probably 12 equations, right? Because we have little information. We've broken this thing up into 3 different sections. And in each section, I can apply these equations. You could do that. I don't know if we have to do that. I'm just talking about what jumps out at me. Because we're going to have to maybe handle the equations, the sections separately, depending on, and maybe the thing that combines them is like the final time in this section is the initial time is in this section. So generally, as I told you, as we've been seeing with many problems we've worked, the ultimate independent variable is time, but that might manifest itself differently depending on what the problem is, or what the circumstances are of the physical situation. But that's just what's jumping out to me right now. I don't know if I'm going to write out the 12 equations for the different sections. I think that might be a little bit overkill in terms of it, because would have to figure out symbols for them. But I'm maybe just apply them to different sections as I see fit. But at any rate, that's step 5. Now, when you get to step 6, you got to be a bit more specific. You got to think about, okay, I need to try to get something. All right, what am I going to try to get? My intuition is just go to the section where I know most information, and then apply those 4 equations in that section, see what I can get. All right. So I think I have all the information here. It just gave us the times there. And well, another piece of implicit information, obviously, is that we know, I've written it in equations, but we know that AY is negative G. And we know the initial velocity here is 0. So V naught, so I called it 0. Um, make sure I didn't miss any information there. The ball dropped from the I did. I was going to say it looks like I'm undetermined, and yeah, I did miss it. It's the distance. The we know the distance of the window, 1.2 meters, and then it falls to the sidewalk and bounces up. So I forgot to write that. I was because just looking at that, I was about to say I'm not sure we can solve this. Like, so I must have missed something. Oh, actually, that's good. That's good. That's good modeling. Because you remember how I told you in step 6, when you get down and you're underdetermined and you miss something. Now I know I probably figured out that we're underdetermined maybe quicker than most of you. Don't worry about that. If you would actually get out and do the process, like I said, you would at some point you would see it. Okay. It's just that I've been doing it, I've been doing it for a while, maybe a little bit more experience than y'all. So don't feel like you have to know something that like I know something you don't know or whatever. No, it's just I can gauge it because I've done it a lot. But if you actually went down for each section and tried to solve for something, you wouldn't be able to. So what I've taught you is that when that happens, you've missed something. Either you've missed a concept, an equation, something. So you got to cycle back to the previous parts of the technique previously. Yeah. So that's how that works. So what was it? Delta Y was let's name it something. Let's call this I'll just call it delta. I don't want to name the section. That's going to give everything a bit too much, but I'll call this guy delta Y. I'll put it over here, delta Y. And maybe we might need to call it something. Maybe we could call it, for now I'll call it delta Y, but if I need to, then I can just do section 1, 2, 3, which means that this will be time. Well, maybe we should go ahead and do that. Let's just go ahead and do that. So time 2, time 3, and this is time 1. I don't know. Obviously, time 1, 2, 3 is going to give the total time. And I'm going to call this delta Y2 just to stay consistent. And this guy is delta Y3, which we know that's 2 meters, right? Or we don't know that. Oh, it's 2 seconds. So we don't know that. And then, of course, we don't know this delta Y, delta Y1. But obviously, that delta Y1 plus delta Y2 plus delta Y3 is going to give us what they're asking for, which is the height of the building. So since I know this distance, delta Y2 is, I still forgot what it was. I don't remember like that. 1.2 meters, 1.20 meters. So delta Y2 is 1.20 meters. So in that section, I guess I don't actually need anything for that section, do I? Because I have the acceleration, I have the time, and I have the distance. Um, okay, okay. It's going at a non-zero velocity at that point, and I know the velocity is changing within that region. Now I could get the average velocity. That's the only thing that I could get in there. Would that help me? Does the average velocity change? Is the average velocity constant? I don't think it is. No, it can't be. Or is it? Oh, that's a good point. Yeah, this is a little bit more advanced problem. That's why they got three dots. I can see that. But I think so. If I come here, I know the delta y, I know the t. That would give me the average velocity. Does the average acceleration is constant? Does that mean that in every section the average velocity is the same? Why am I drawing a blank on that? I taught you was when the acceleration is zero, the average velocity and the instantaneous velocity is the same in the x versus t curve. But the average velocity can also be written as delta v over delta t. That's actually it. That is it. The average velocity is the same when the acceleration is constant. That's actually the definition of constant acceleration. You can actually see it in equation one, right? And we defined it actually. We defined it. We said that acceleration is equal to average acceleration is equal to delta v over delta t. I did that whenever I derived this equation, the definition of average. So when the acceleration is constant, the average velocity, it means, like basically from this equation, this would be vy naught. From equation one, I should probably say that. So that's what makes this problem difficult. If you don't realize that, there's no way to do the problem. When acceleration constant, the average velocity is also constant. Yeah. Wait a minute. That's average acceleration. Let me back up. Average acceleration. So average velocity delta v is equal to delta v average is equal to delta x over delta t. That's average velocity. And a average is equal to delta v over delta t. Let me back up a minute. I might have misspoke. You know what? I think I'm going to have to do what I said. I can't see it from here. I'm going to have to make the equations specific to each section. I'm just going to have to do that. Um, I really can't see it too much for me, too many equations to see what's what and how to negotiate them. So one way that I can do that, I want to make this section 2 and go through and do that. So I won't need the subscripts y because we know that it's in the y direction. So I'm going to make them specific to the different sections 1, 2, and 3. And we're going to do it like that. So this is section 1, section 2, and section 3. So let's do section 2 right now. So in section 2, this is going to be, and we'll do the trip going down. So final means when it gets to the bottom of that section, and initial is when it's at the top of that section. So so if this is section 2, well, I'll put like section 2. So V2 equals V2 naught minus G2. Here, I made that even more complicated. I guess we could do, I'm just going to do the delta y. That's easier. So if I bring this guy over, because that's all I need is the delta. So if I bring this over, that's a delta y, and that's delta y2. So this guy is going to be dy 2 naught, and then delta y2. And then this guy is delta y2, and this is going to be v2 and v2 naught. It doesn't matter. I think I switched it around. I mean, this is also t2. Okay, that's section 2. Let's go do section 1. Now, section 1, same equations, right? But we're going to have some zeros up there because of the initial velocity up there. So section 1, okay, V1 equals V1 naught minus GT1. 2, delta Y1 equals Vy or V1 naught, which is 0 times T minus 1/2 GT1 squared. By the way, I didn't do that one. That's V2 naught. Then V1 squared equals V1 naught squared, which is 0 minus 2 G delta 1, delta Y1. And then finally, delta Y1. Actually, I should have kept these numbers. So keep the numbers going. So 4, 5, 6, 7, 8. Now delta Y equals 1/2 V1 1 naught plus V1 times T1. While I'm at it, I just found I might as well do the last one too. So section 3, right, the temptation is always to feel like you don't need to do something, but whatever. That kind of can lead to just do it. So 9. So now I'm in this section, and I have V1 V3 equals V3 naught minus GT3, and then delta Y3 is equal to V3 naught times T3 minus G 1/2 G T squared, 3 squared. And then delta Y3 equals 1/2 VY3 plus V3 naught, that is, plus V3 times T3. This is 1. This is section 2 and 2. Now, a couple things to realize, I'm going to put these over here, is that at these boundaries, so first of all, that guy is 0, so we can go ahead and take that out. Let's go ahead and do the zeros on that. So that's 0, that whole term is 0, that's 0, and that is 0. So those equations will simplify. And also we know that, well, I might need that space over there, so do this. We know that V2 equals, so V1 equals V2 naught at the velocity here. And then V2, the end of the velocity at this section is equal to V3 naught. So that also simplifies some things. And honestly, usually with these things, I just go for the jugular, right? And then see what pops out. So the jugular, and also knowing that the equations that are parabolic in time for the 4 basic equations for free fall motion are always the most powerful equations because of the parabola. I've told you that. So the equation 2, equation 6, and equation 10 are the most powerful equations. And those are the equations that if I add them up, I get what I want. So just as a procedural, I'll say, okay, well, you go for the jugular. So if I get delta Y1 plus, let's call this equation 12, and then equation 13, equation 14. So delta Y1 plus delta Y2 plus delta Y3 equals basically, I don't know, call it H. Let's say that's the thing we want, is just the height of the building. Then that's that's what I would do. Just go ahead, write out and add the equations together. I mean, I know I'm not going to have everything I need, but that would show me then what unknowns that I need to solve for to plug into that. That's how I would approach the problem. So let's just do that. So then equation 15. So H then is going to be equal to this thing, which is going to be V2 naught T2 minus 1/2 G T2 squared plus this thing, which is just, sorry, I know I never. So delta Y1 is this guy. So that's going to be minus 1/2 GT1 squared, and then plus this stuff, which is V3. Let's do it like this. V3 naught T3 minus 1/2 GT3 squared. I got a lot of unknowns in that. Let's mark the unknowns. Well, let's actually mark the knowns. The only thing that I know, I've marked that in blue, is this time. I know that time, I know that time, and I don't know anything else. So I do know that That's the same as V1 and the V2. So I know this is V2 right here. I do know that. Um, yeah, that's a lot. Well, that's not so helpful. I mean, it is to some degree, but not what I thought it was going to do. Well, there's only one other way that we can get the total distance. Um, we have several unknowns in that. The unknowns are 1, uh, 2, 3, and 4. And also, this is an unknown. That's 5. Yeah. So if I were to look at, there's another thing I could do is I have the delta y's in equation. Oh, I missed an equation here. So let's call this equation 12. And the velocity squared equation for this, I'll call it 11. Let's put it here. The velocity squared equation is what is it, section 3? So V3 squared equals V3 naught squared minus 2G delta Y3. So I tried to find the distance with those guys. Then I've got, that's going to bring it back to the same thing. So that delta y, so if I add this delta y, that delta y, that delta y, like solve this for this guy, solve this for delta y, that's going to be field velocity squared over 2g. So that's 1, 2 here. I don't know those velocities. I do know that distance. That velocity there is the same as this guy. Adding those together, this is 1, 2, 3, 4, and here, that's just 1. But I also don't know that distance. And actually, this is 1, 2, 3. I don't know that. And 4, 5. 1, 2, 3, 4, 5. And one of those is reduced, so that's just 4. And then up here, 5 and 6. So adding those together is not, that's going to be kind of, I can't use that over here, can I? No, because that's just going to get me back to the same equation because that's derived from eliminating t between those two. Okay. Well, I'm back to actually this is a good illustration. I think I know what to do. It was my first inclination. I think that's how you got to do this problem. My first inclination was that the average velocity is the same everywhere. The average velocity is the same in each section, which means that even though the velocities are different and the times are different, the delta V's over the delta T's, I mean, you can kind of see it right here, right? If I take, is what I was going to say, but then I got a little sidetracked, but whatever. Um, if I take this, I have V uh, 2 minus V2 naught divided by T2. Well, that equals negative G. That's a constant. And negative G is the same in each section. So what that's saying is that, you know, uh, well, that's the average acceleration. I'll keep saying that. Average acceleration is not average velocity, but average acceleration, when the average acceleration is constant, well, it's kind of what I said with velocity. I remember there was some problems we did where I said, like when you draw when you look at the x versus t curve, right? And you say that, so you got a constant line. Well, obviously the velocity is constant. But when the velocity is constant, the average, yeah, that's it. When you look at the x versus, because I didn't do this in class, I told you that it was mimicked it. So let's say that this is x versus t. Um, we know that if we have 2 points, x1 and x2, we spent a lot of time deriving the average velocity, then taking the limit of the average velocity that became the instantaneous velocity. But here in the x versus t curve, the average velocity is constant. Why? Because the velocity is the slope of the curve and the slope is constant. So whenever the velocity is constant, then the average velocity, that is, if I find the velocity at this point and the velocity at this point, sorry, the position at this point and the position at this point divided by time, anywhere on this line where I do that, it's going to be the same as the instantaneous velocity. Well, you have something like that similar if you plot the V versus T curve for a constant acceleration, right? Because if you plot that, mathematically it's the same, except that now we're here, the slope was equal to, you know, the average velocity. Here, the slope is equal to the average acceleration, but it's constant. So the average acceleration and the instantaneous acceleration are the same. So you can make an analogous argument that if I come here, right? So this is, sorry, this was T1 and T2, and this was X1 and X2, right? So then V is equal to delta X over delta T. Well, same thing here. This is still going to be T1 and here T2, but this is V1 and V2. So the slope of this curve is the acceleration, but as I said, the average acceleration between any 2 points along the line is equal to the instantaneous acceleration because it's constant, and that's g. And that is the delta v. That's v2 minus v1 over basically delta t is equal to that constant. Well, we don't know what it is, but it's equal to that constant value a. That's the key to this problem. So that was my initial inclination because that's the only thing we can figure out from the information they give us. And the other thing about that, and I think I told you on the first week, or maybe when I was deriving these equations, that one of the hard, even though, and this is why I actually write 4 equations of motion, not 3. And some books just do 3. I always put this one in here that you very rarely use, right? Because you're always doing what I was, starting to do, manipulating the other equations, looking for knowns and unknowns. but we can't use any of the other equations in any of the other sections. The only thing that we can do initially, that is initially you can, is use this equation in actually all of the sections. But you would never do that if you didn't know that this thing that I'm saying here. So that's what we have to do. We have to go, and let's go to this. Let's go to, because the only section in which we have enough information to figure it out is section 2. In fact, the only thing that we can figure out initially is the average velocity, and we can only do that in this section. But then, if we realize what I just showed you here, we realize that that's the same average velocity in each of the other sections. So now we have new information that we can go to the other section using the same equation, the fourth equation, and then solve for the unknowns that we see there. So that's how to do the problem. Yeah, this was a tough one. But now there's a pattern, because usually when you do, like I've pretty much went through a lot of the iterations. I didn't go and look at this equation here. I looked at basically those two because they had the distances in it. But I could see that if I can't get it here, then this is not going to really help me, right? Because this is a combination of these two anyway, right? So I just did it in my head, right? I added up, I solved these for delta equation 3 for the delta y in each section. And what I realized is that when I add them together, I'm going to get something like this where I'm still underdetermined. So the only thing that I haven't used is this guy in each of the sections. And that brought me back to my initial impulse, which I was a little bit shaky about because I'm a little bit rusty. I had, and I thought maybe that wasn't the case. And then I tried to see if I could solve it just analytically some other way. I couldn't. It took me back to basically the only thing that was left, which was the equations that I hadn't used. And then that made me focus in and prove to myself, as opposed to going back and reading through, to make sure that my inclination was right. And it is right. That the average, when the acceleration is constant, the average velocity in each section, basically the average velocity is constant. So that's how we have to do it. That's how we have to do it. So, the past couple of days, I mean, I will solve the problem here. I'll do it. I'll finish out in a minute. But I just want to reflect, like the past couple of days, it just so happened, that the problems that came up in class were somewhat difficult problems. But again, this is why it's not necessarily a bad thing if I can be transparent and show you how I work, how people work. So some version of what I just did, you got to learn to do that for yourself. And the only way that I know to do that is I just showed you. I practiced the technique. And even if you don't know how to do a problem, you can figure it out. That's as good as it gets. So let's go in. Let's go in and do it. So I'm going to go back. I need some space. So I'm going to go back and erase all the stuff where I started, because I'm going to start back with, basically with this equation here, and then go from that to the other sections. So I want to take that out. This is kind of nice here. I told you, I didn't do that in class because I wanted to move on the graphical stuff, but it's analogous to this thing. So, yeah, a little messy here, but let's just go ahead and jump in. So yeah, I have enough information here, because the other thing that I want to show you is that in this case, this is the numerical average, right? But we did that in the first or second week, that there's two definitions of, in fact, that's how I derived this guy, I believe. There's two definitions of average velocity. There's the physical definition, average velocity equals v final minus v initial divided by delta t. But there's also the mathematical definition of an average, that v average is equal to 1/2 v final plus v initial. Even though they're different mathematical, different formula, they give the same number. And I used that whenever I derived, I forget which one it was. I think it was this one. Oh, what? Yeah, I used I use these three equations and this guy to derive this. We've seen it before. But again, what's also a little bit deceiving is that when you come down here to write this average, what I call the average, that's why I call it that, the average velocity equation, is because it has the numerical average in there, which is really isn't a physics equation, but it could be replaced with this. I don't do that because that's how we got to there, was using that to kind of take it out. But the point is that the value is the same. Value is the same. So I can use this equation in section 2 to calculate that number, realizing it's the same number from the physical point of view. Right? So then I can go and use that in the other sections, that value, because that's going to be the same number here. Here for section 3. Sorry, 1/2 has got to be in there. Here for section 3, and here for section 1. So that'll be a known value now. So if we then calculate that, what do we have? We had the distance, so let's just calculate it. So from equation 4, so 12, so 13, 14. So then delta y2 times 2. Well, it's the average velocity, so I'll leave the 2 in there. So delta y divided by delta t equals, and you can see it's just the definition, it's equal to going to be 1/2 v2 plus v2 naught, but that also equals basically the average velocity for that section, which just equals the average velocity period for all the sections. So I'm just going to call it delta b. And when I put the numbers in, the average velocity then is I don't know, what is it? Um, 1.20 meters divided by 0.125 seconds. One 0.20 meters divided by 0.125 seconds equals whatever the number is. So we're going to get 1.2 enter 0.125 divided by average velocity is 9.6 meters per second. Okay, so I'm going to underline that. Think about that again. So mix up the numbers. 1.25 seconds in that section. I know the total distance it falls through. That's it. That's how to do it. So now, so what I want is the distances. Let's see if we can go directly. And so I'm saying this number is that same number, 9.6. But I don't know. Yeah, that's going to help us now. Because I don't know. Now we can do the knowns and unknowns just on that fourth equation in each of the sections. I think that's going to be more useful and give us some insight as to how we need to proceed. So I'm going to mark the unknowns in blue. So this guy is unknown. That's what I want. And I don't know the time in section 3. Up here, that guy is an unknown. And I don't know the time in section 1. But I know the total time between this section and that section. Yeah, I might have to make some new equations using combining sections like that. I could just, so delta y1 and delta y2 average velocity. Well, I also have this equation here because I can get that time. So oh, duh. I do have the time. I'm sorry. I do have time 3. Sorry. Sorry. So that's it. Sorry. That's not an unknown. Amen. So that's it. That's going to give me delta y3. Sorry about that. Yeah. I mean, it gets confusing, right? So, that's why you want to have the information out. Like, if I hadn't written that up there, I would have been spinning around here for the next 40 minutes if I hadn't put all the information up there. So I found it. So yeah. So now, the only unknown is, I think I said I was marking the unknown. So I'm going to mark the knowns. I had started doing that in red, I thought, but that is a known value, right? Because it's 2 seconds. So now that I know that the average value is the same, I put that value in here and I'm going to get that distance. And so that'll give me that distance. So I have those two. And this is the holdout. And that was the thing that I knew least about. But I do know, I think I'm going to have to then use, I think I might actually have to get a velocity. Let's see. So I definitely got that distance right there. Now, when I come up to section 3, I'm trying to get delta y, and it's here and it's here. Now I know this value, but I don't know that this is where I have the two. And I don't know that guy, and I don't know that guy. Up here, again, I don't know the time, and I don't know the delta y. But if I could get this velocity, then I could get that time and I could get that distance. And I think I can get that velocity because that final velocity there is the initial velocity here. But now I have all this information for this section. Now, I think I can do it with average velocity. Oh, no, 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 no. That's not how to do it. Yes, do it with average velocity, but I have to use this equation. It's not going to be a physics equation, right? Yes, that's it. Yeah, this is tough. This is a tough problem, I admit. But that's it though. Look, I just said I have the average velocity, and I have 2 types of equations for average velocity. I have the physics equation, but I have the numeric equation. In this section, v1 naught is 0. So this guy in section 1 is 0, but I know that number. That's this. So put that in this equation, solve for v final, which is what I called v1 over here. Put v1 in that equation, get t1, take t1, put it in here or here, and get delta y1. And that's it. I have them all. Delta y1 plus delta y3 plus the 1.2 for delta y2, and that's it. That's it. So we can do that, and then I think it's an even number, an odd number. We can check to see if uh, if the answer is what they have in the book. But you know, I might make some numerical error here in the process, but there is no other way to do this problem. You can clearly see we exhausted everything. So this is the kind of problem, I'll tell you, this is the kind of problem that honestly, I couldn't really do them with confidence, back when I was where you were. And the reason is because how you could clearly see I've been completely transparent. You clearly see my process. I did not have that process when I was an undergrad. And when I started teaching, I couldn't, like at some point you might kind of develop an intuition and you kind of figure things out and you know what you're doing. Okay, that's a level up from not really and being somewhat consistently being able to do that. Okay, that's where you want to go. That's a level up from kind of hitting and missing and whatever. But then another level is how do you teach that to someone? You can't teach them like they ask you, how'd you know that? Like I just knew it. Like that doesn't help them. It's not going to help you if I'm just doing that. Yeah, it shows you that you're smart, but the person wants to learn how to do that. So when I started doing that in grad school, started tutoring and teaching that, then I went back and really assessed why did I have so much difficulty? And what I realized is I didn't have a solid technique that I could go to every time, such that every time at work, I got more confident in that process and because I got the right answer and I got more confident in my ability to do the material. Having something like that is teachable and it makes you more self-aware of why you're getting things right and what you're doing. So I haven't done a problem like this in a long time. And I like to just kind of sometimes, which is what I did, is dangerous and can be embarrassing, where I just pick a problem, from a book, regardless of how difficult it is, and do it for students because usually I do it at this level of the class, at least once or twice. And I know it takes a while, whatever. But I want you to see that what I'm telling you is true. Like this thing will work. And again, you can tweak it for whatever your sensibility is, but you got to have a technique in order to be consistently, getting problems done and correctly and, and build your confidence and move on. So I hope you're convinced. And yeah, let's get the answer and then take a break. So I don't think I need all this other stuff, so I'm going to erase some stuff to clear it up. And I say hard. I shouldn't judge it like that. Just, it's a lot of record keeping and things, a lot of equations. You have to look for the unknowns. But there was some physics in there. That little physics about the average velocity, that's the trick for this problem. That's the eureka moment for this problem. And if you don't get that, you will never get the problem. And it's not really mathematical or equations, it's actually physics. It's a very subtle thing about the physics of constant acceleration. So, yeah. So let's go. So we got 9.6. I need to store that. I think it's exact, actually. Yeah. So store 0. Zero register. Now I'm going to take that and put it into this guy. And it's the whole thing. You don't need the 1/2. It's the whole average velocity because of this relationship here, right? So it's just the 9.6 times T3, which is 2 seconds, is going to be that distance there. So that distance is going to be 19.2 meters. I'm going to store that in 1. And we can come up here and write them on there. So I'm saying that, actually we can write them in here. This distance is 1.2 meters. 1 meters. Now I'm saying this distance here is 19.20 or 19.2 meters. And this is the last holdout. Now, how do I get that? Again, so I've exhausted all the other equations. I'm just in these four now. I only got two options, this equation or this equation. In both of them, the time is the unknown. I mean, the time and the delta y are the unknowns. So it looks like you can't solve the problem because you come here, you still don't know this, and you also don't know this, right? Again, so I guess there's two things that you can't do if you do the problem. One, realizing that the average velocity is the same in all the sections because the acceleration is constant. But also the other subtle thing is realizing that you can equate the average velocity equations, the physics one and the math, the arithmetic one. Because again, if you don't even see that when you get here, there's no other physics equations to use and we're out. But we can use that equation to get the thing that we need. So let's do it. So then if I using that equation, V1, as I call it, is going to be equal to the average velocity times 2. And that will be equal to, so the V1 is this guy, and I guess that's it. So the final velocity yeah. So I'm getting that to be V1, make this 16, 17, getting V1 to be 2 times 9.6, which is equal to 19.2 meters per second. Meters per second velocity. Okay. So now if I take that velocity, so that's got to be 2 seconds then. No, maybe not. So now if I take that velocity and put it in here, that's going to give me time. Actually, I could just go directly because can I put it in here? I can. I don't have to find the time. I can take that velocity and use this equation. And so then that's going to give me that delta y1 is going to be equal to v1 squared divided by 2g. So delta y1 is equal to so 19.2 quantity squared divided by 9.81 divided by 18.78 meters. 18.7, 18.8. 18.8 meters. Let's store this in register 2. Let me just check or think about that again. 18.8 meters. So if we add them up, we should have the total height. I'm going to check through this again. Maybe one of you can look that up and see if that actually gives us the right answer. Just let me think through it again before I do that. I'll box this in, and this was equal to, we say 19.2 delta y 3. Put that in, and we were given that distance. Seems odd that yeah, I guess the window would be small compared to the other distances. That makes reasonable sense. All right, so we started off with section 3. Here we talked the average velocity. We're using the fact that the average velocity is the same everywhere because the acceleration is constant. That does make sense, even qualitatively. I don't know why I question that, because acceleration means the increase in the speed, but the speed is increasing the same amount in the same amount of time over the same amount of distance. And acceleration, yeah. So actually, it's not over the same amount of distance. It's in the same. Is that true? What am I saying? Yeah, the increase in speed. Yeah, it is. Yeah. So, yeah. Anyway, we took that. We used that knowledge. We found the value of the average acceleration, and I used that to get the delta y over here. Because I knew the time, it gave me the time. And then the most difficult thing was getting the distance up here, because down here, I don't know the time. And so that third equation doesn't help me. In fact, none of the physics equations really help because I'm always underdetermined. But when I use this relationship, the algebraic definition of velocity, it allows me to get, because initial velocity is 0. See, I couldn't do that with this because I don't know the time, but I could do it here. It gives me the final velocity at the end of that section, which is what this is. Then I could use that. It doesn't ask for the time, but I could use that to get the time. But what I really want is the displacement here, so I can take that value, since this initial velocity is 0, put it here, and that will directly solve for what that delta y is because of this equation here. I'm just going to check my numbers again, and then we'll see. So I start off with average velocity. It's total displacement over total time. Displacement is 1.2. 1.2, enter 0.125, 9.6. And then 9.6, average velocity, same here, times 2. 10.2. 9.6 times 2 is going to give me 19.2 meters per second. Don't get that twisted. Sometimes you can. I just calculated meters over here, but this is velocity. So now taking that velocity and putting it into the velocity squared equation, we're squaring that velocity, dividing by 2g, using 9.81 per g, gives me that distance, which is 8.77. So if I add them all up, I would say that the total distance, of the total height h of the building, I've erased that equation, but it's just the sum of all those, delta y 1 plus delta y 2 plus delta y 3, h is equal to. So I stored all that stuff, so I'm not truncating. I'm going to go back and use all the stored values. 19.2, where did I store that? That's the one, I think. So let me call 1. Yeah, plus. And the 1.2, that's just 1.2 exactly. So 1.2 plus. So I get a total of the 3 significant digits, 39.2 meters is the height of the building. Did anyone look it up to see if that's an answer?
I think the answer is 20.4, but
Really?
might be wrong. Yeah.
Is that what that's what it says?
Yeah. So I also realized that if you take 39.2 meters and then subtract that by 18.8, you get 20.4 meters, which is what the book says is the answer.
If you do what now?
Like, I don't know. Okay, so I noticed that if you take 39.2 meters and then you
Hmm.
subtract that value from 20.4 meters, or no, sorry. You take 39.2 meters and subtract that value from 18.8 meters, and then you get 20.4 meters. But I don't know how that makes sense.
Maybe I'm finding the wrong thing. Are they asking for the height of the roof or the height the where the top of the window is from the ground?
You know what? Actually, let me
Maybe I
check.
misread that
What up?
because I might have misread that.
I'm trying to go back to the prom right now. Like,
Okay.
oops. So it says how tall is the building? Okay. I'm just like rereading the question right now. Yeah, I'm not sure.
Interesting. Because basically what you're saying is that the height of the window, because that's what this point is this distance plus that distance, 1.2 plus. You said 20.4 is what you said is the answer is?
Yeah.
You know what? I think they made a mistake because that doesn't make sense.
Mm-hmm.
Um,
Because it doesn't say like find the height of the building from like the bottom of the window or anything, right? Because if it said that, then it's I think it'd be 20.4, but it doesn't like specify that. So
well, let me say I'm saying that for a different reason why I don't think it makes sense. That could be, I can see how that could be maybe a mistake. Not a mistake in the answer. Like the answer is not wrong necessarily, but I could see how someone could get confused and answering the wrong thing. Because they could have asked you that. That was a valid question. Like, how far is the roof above the ground? I mean, so how far is the top of the window above the ground? You basically have to do everything we did except for the last step, right? You still have to do all the stuff I said. You get 19.2, add that to 1.2, and that's right here. That's the 20.4. That next step is a little bit more difficult for what I said, but I guess this is what I say that because there's nothing that we did with the top of the building that was used from information. We didn't use any information of this stuff here to get this down here, right? I used just the average velocity of this, which is valid. I mean, I don't see how that could possibly be wrong. It's just the average velocity. Now I use that in this section and just use that time. I just literally took that number and multiplied it here. And so there's a coincidence. So I don't see how this could be anything but 19.2. Like
mhm.
what else could, you know what I mean?
Yeah.
Um, but then coincidentally, when you add that together, you get that number that they have. That
Um.
suggests to me that, say
Yeah,
again?
I think so. Wait, hold on. I'm just doing the math in my head right now. I think you're right though. Yeah, that's the answer. If you add 1.2 to 19.2, you also get 20.4.
Yeah. So that suggests to me that the graduate student just wrote down the wrong answer. Not the wrong answer, but the answer that wasn't asked for, that is also a valid answer for whoever was working that problem. Where is the answer, by the way? Is in if you're looking at the back, do they give the solution or do they just give the answer?
It's just the answer. And I also found that like on the online textbook, if you go like if you scroll so I was in the a table of contents. If you scroll all the way down, there's
Mm-hmm.
a section called answers to checkpoints and odd number question problems. Click
Mm-hmm.
that, and then I just scroll down to chapter two, which is where this problem
Mm-hmm.
comes from. And then yeah,
Mm-hmm.
chapter two, number 61. Yeah, it says 20.4.
Yeah, but it doesn't give a solution though.
Yeah, it's just the answer. That's it.
Yeah, I don't have a solution manual for Halley and Resnick. They do exist. I just don't have that. I never had it. But that would tell if we had the solution, then probably its chances are in the solution, it might have they would explain or show that that was the answer. But I don't see how that could possibly be. I mean, how could that like the only way that could be is if this number is somehow shorter. But how? Like what? Like there's if you you don't again you don't need anything from this section to get this stuff down here. You have enough information. So let's say like let's just troubleshoot. What could I have done wrong? Well, since I use the average velocity here, it must be too fast. So I must be able to get it some other way. Okay, what other way? Like you can't get anything from any of that information. That's what I went through the first that all that long stuff that I went through. I thought you might have. I wasn't. I didn't think. I was just following the technique. But when I tried to do that, there's no way. Like I can't get the time. I can't get anything here. Possibly, what about this section? Well, in this section, the problem there is I don't know the initial and final velocities. So the only thing that I can do is get the average velocity. There's nothing else. So with that average velocity, I see that I could get, this distance here. I still don't know the actual individual velocities, but if that's wrong, it's basically saying that somehow this is too large, and which would imply that this is too fast. Okay, then what else is there to do? There's literally there's literally nothing else you can do anywhere with this problem with the information given. That's why it's a difficult problem. So my inclination is that we didn't do, or I didn't do anything wrong. And especially with the coincidence that there's a number there that's right, that's what a number that I'm getting with correction. And y'all know, well, it's not Wally, but I was going to say if it was a Wally, you know how stickler they are. But it's the exact same number, which means, and I did take all the significant digits in correctly the way you're supposed to do it, and I get that exact same number. That just simply tells me that the graduate student wrote down the right answer for the wrong thing because there's nothing else. Now I
Mhm.
could be wrong, but I would go with that, and I would defend it to anyone. Now we'll see. Maybe you can keep looking for a manual somewhere. I'll try to look around see if I can find some. I could be doing something wrong, but I don't know what. So this is just the kind of confidence you got to get. Like, and it just takes time to get to there because that's not really fair. They should have a right answer. They should have made a mistake on a difficult problem like this because it still can kind of shake your confidence, right? If you don't. But I did everything. I literally went through all the other, like, there's nothing else you could do. So that and the fact that at least there is a number that they have suggests to me that's an error on their part. And that's why. Let me see if I can think about it some other way. Oh, I know how we could check it. I know how we could check. No, maybe not. Can you hear me?
Yeah.
Cool. Uh, so they're saying 20.4 is the roof. That's because that's what is asking for the roof, right?
Yeah, I was asking, I'm just gonna triple check real quick. Why not? Just to make sure that the right
Yeah,
idea.
they did say that. I think they said the height of the building. So
It
yeah.
says how tall is the building? So yeah, you'd assume that it goes to like the roof.
And we're assuming that the window, because I have a space between that. There's nothing in the problem that says that the window is flush with the roof, is it? I mean, because they can make that approximation.
No, yeah, it doesn't say
No.
anything like that.
um, since they didn't break down, like I don't. Yeah, we don't have enough. Yeah, I don't. There's not. I don't think there's enough information to be able to check because they didn't give us like what they have the values, interim values or anything like that. Yeah, I'm gonna go with that. Um, I mean, if I yeah. So this is a kind of a signature. A hint. I don't know why I didn't catch it earlier. That whenever you have a problem like this, I think I did say it, but third time I'm saying it. That's why I like to put the average velocity equation because you usually need it when you need it. The times that you really have to use this equation, it's usually a difficult. I think I said that on the first week. It's usually a pretty difficult problem, and this is an example of what I mean by that. Because there's nothing else that you can use to get started, or even to track through, because they don't give you the velocities. Uh, you know, and once you have it, though, you can go back and calculate them. Now you get the times, but um, and so when we have this first velocity here. So yeah, man, I don't. I think I disagree. I disagree with that. I disagree with that result. I think that that answer is the top of the window from the ground, not the roof from the ground. And the only way that that could be true is if the window were flush with the roof, which, maybe an ideal case, but they didn't say that. So I don't think you can assume that. You read the problem again. A steel ball is dropped from a building's roof and passes a window, taking 1.25 seconds to fall from the top to the bottom of the window, a distance of 1.2 meters. It then falls to a sidewalk and bounces, blah, blah, blah. You know what? I think you could interpret that either way. A steel ball is dropped from a building's roof and passes a window. It doesn't say anything about that. You know what? I think that's how they're interpreting the problem, in which case, technically, they're not wrong, because I think you can interpret it either way. It's it's two options of doing the problem, but that's an easier option. That's an easier option. I'm reading the problem again and looking at it from that point of view. That that um Kimberly, did you say, well, Kimberly Michelle, what happened with the yes? I didn't that. What was that about?
He asked us, could we hear you?
Oh, okay. Okay, thank you.
Yeah.
Yeah, yeah, I think you could probably interpret the problem like that. You certainly could. There's nothing in that problem that specifically says it falls a distance before it gets to that window. It doesn't say that. I mean, I would assume that it does because that's what most buildings do. But if the per that's an easier problem. It's an easier problem because it just takes us to here from this step to this step and we're done. This step is a more difficult step, a little bit more, but I think this is more realistic. And so that's why I'm giving that answer there. That's all I got. That's all I got. I think this is the way to do the problem. Let's take a little bit of a break and come back. We'll do one that's not so difficult. I'll pick one. I'll take one from my notes because there's several other kinds that we can do that are a little bit more straightforward than that one. But still, I think that is what it is. Let's take a little break.
I'm sorry, really fast. Was this from the was this problem from the homework? What number was this? I can't find this problem.
It's in the textbook. It's this guy right here. So this is in your textbook in the back of the chapter of chapter 1.
Oh,
This problem.
chapter 1.
It's chapter 2,
Yeah.
actually.
Oh, it's chapter 2. Sorry. Oh, it's chapter 2. Oh,
Yeah.
chapter 2. Yeah, because it's the chapter on one-dimensional kinematics, right? It's chapter 2. So yeah, number 61. And I
Okay.
think I chose the 3 dots because those are the harder problems, and it really was kind of a hard problem. But you know, yeah. So that's where that's from. Okay. I just chose it. I just chose an arbitrary problem to work with from the book. I hadn't looked at it before class. That probably should have. All right. Hello.
Yeah. Okay.
Yeah.
I'm just gonna taking a look at it in my book and trying to see if I can figure it out.
Yeah. All right.
It's okay. Basically.
Kimberly, you're not muted.
Oh, I'm sorry.
Yeah, I wanted to make sure,
How long have I been like that?
like 5 minutes, 10 minutes.
Oh, thank you, boss. I appreciate you, man.
Hey, Kareem, thank you, and good question. Yeah, the the test questions are from the same question bank as the quizzes. So, from what students tell me, that the quizzes are not as quite as difficult as the Wiley Plus. So that implies that perhaps those same people might feel like the test questions are not as well. There's more, than just a few questions, but I get them from the same question bank, at least up till now, and I will continue to do that. I won't be getting them from Wiley Plus, but I actually have my own questions that I have. It's taken a lot more time to try to incorporate those into the. I haven't done much of that yet, and probably won't this semester, but that's where I'm getting the test questions now. Cool. You there, Kareem?
Professor, I also had one question.
Yeah.
I notice a lot of the times, like the like the book or the questions, like the gravitational constant they're based on is 9.8. So sometimes it says to use 9.8, but then other times you're using 9.81. But then sometimes that varies the calculations a little bit. How am I supposed to know which what to use for G?
Yeah, I mean, I set a convention that I always use 9.81. I think most books do that, but
Well, I solved this question that we were working on, so I get similar answers, but I think they're a little bit different because I'm using 9.81 and I think the book is using 9.8.
really.
Yeah, and for the for because the equation that we would use to solve it is the x minus x naught v naught t plus half at squared,
Hmm.
and then solve for like our initial velocity. And then when we set that up, we would set it up as what is it, y2 minus y1 v1 times t2 minus t1 plus 1/2 g times t2 minus t1 squared. And then when we solve for that, it gives us the value for v1, which is I think the uh, 8.98. And then we take that, and then there's another equation for constant acceleration, which is the figure, I think 216, the equation 216,
Hmm.
which is the v squared equals v naught squared plus 2a times x minus x naught. And then when we put our values in there and we solve for y1, we get 4.11. So when I take those two values and then I finally do it, factor in y3, at the end I get 20.43. So it's consistent with the solution in the book.
Are you
But I
talking?
think,
You're talking about for another problem. You're not talking about this problem, are you?
yeah, that's the problem I'm talking about.
Oh, okay. I'm sorry. You kind of threw me off there. I thought you were talking in general about. Okay, so yeah. So you're saying my numbers are off a little bit from what
I don't know where did you get that 18.8 meters from?
I got that from calculating the using the average velocity to calculate the um so I first calculated the final velocity because it starts from zero, it falls here, I found that velocity using the average velocity equation. And then I took that final velocity and put it back into this equation to get the, well, actually, no, I went directly. I put it into this equation to get the distance that it had fallen through. So that velocity, this final velocity here squared times 2 or divided by 2g equals this distance. So that's where I got the 18.8.
Yeah, because
So
I think that the
go
way I
ahead.
calculated it, that distance, let me see if I can find
So
it.
you kind of threw me off here because you were talking about one thing, and then I thought you were just giving an example, probably where that happened. But you're saying this example. But so there's two things. Let me just answer the first one first. You
Yeah.
asked me what you use, 19.81 or 19.8. I always use 9.81. And if you get like that's going to be within the tolerance usually, but if it's not, then because Wiley is a little bit stickler. I've been saying this, I'll say it again. If you get like some answer and it's slightly off and they take off 8/10 or 9/10 of a point, just write me and I'll give you the credit back. I'll go and check it and give it back. That should make
Yeah.
a difference on that much of a difference. But I think most people use 19.8, I'm sorry, 9.81. So that's the answer to that question. Now, because I was trying to focus on that, what are you saying about this?
Oh, I'm saying when I solved it, like my answers are somewhat consistent with what's in the book, but I think it's just that I used a different constant for I think if I use 9.8 as my number, I'll get the same numbers
Same numbers as what?
as the solution. I got 20.43 meters tall for the height of the building.
So, okay, so can you explain to us how you did that? Why you think it's 20.4 and
Yeah,
not, okay, go ahead.
yeah. Okay, so when we're when we're setting up the equation, what I did was I took I set V1 and made that equals to the 1.2 meters minus 1/2 9.81 times the time squared, so 0.125 seconds squared, and then put that over the time, which is 0.125, and that gives me 8.98 meters per second
Okay, stop
for
right there. Stop for the for the velocity, we're here or here.
this is for V1. So up
Okay,
there.
so here.
Yeah.
Okay, so let me ask you this. Okay, okay, I'll go with that. I'll go with
So
that.
then so then once I have that velocity, the 8.98, we use the equation where velocity squared equals v naught squared plus 2a times x minus x naught, which is the one of the uh like I think it's what, 5 equations
Yeah,
for
yeah,
constant
right. It's a
acceleration.
velocity squared equation, yes.
Yeah, so using that, I solved for y1, so the distance y1, and that gives me 4.11. Let me see exactly what it gives me. 4.1165 meters. And then
For this distance here?
yes,
Okay.
and then what do I do? I take uh, Yeah, so then I take T3 minus T2, and that's so my final equation, the way I set it up was to find the total height is going to be y3 minus the 4.1165 meters equals or 8.98 meters per second times the time that we got from the from the difference, which is 1.125 seconds, and then you add the gravitational constants, half times 9.81 meters per second, and then multiplied by the time squared. So it's the same equation that we used in the beginning. The x
So
minus
posi-
x naught equals v naught t plus half at squared. And then that
Mhm.
gives us our h, which is 20.43 meters as the height of the building.
Did you calculate this distance separately? I didn't hear you say that. Did you do that?
Yes, because the height of the building, we look at that as y our third value for y. So like the total height, or like yeah.
So what did you calculate for that? So you're saying that once you got the total height, you're just going to subtract that total height from this distance to get that. So you got whatever distance you got for that. You got
Yeah,
it
because
from
we got
after
y1.
you got the total height. That's what you're saying.
Yeah, yeah.
Hmm. Well, I have to admit, I don't. Just listening to you right there, I don't see anything wrong with what you did. Let me repeat back just to make sure I understand what you're saying. You said you started here and you used the position equation. Delta
Yes.
y equals v naught y, v naught t minus 1/2 gt squared. And you're right, actually, I didn't see that. The only unknown in that equation is the initial velocity. So if you know the distance that it falls through, what you do is 1.2 meters. And
Yeah, so
you
we can
have the
solve for
time.
that initial velocity, and then once we get the initial velocity, we can determine the distance from the bottom of the window to the top of the building. So we have that we can determine that uh or at least the y position of where that is.
Yeah, you have delta y, and you got 4 point some meters for that, is what you're saying.
I got 4.1165 meters, yeah.
What did you get the time? What did you get for that time right here?
That was already a given, right? That was one point. What was
No,
that?
the time for the top thing up here. Oh yeah, that's the problem. That's the problem with that. Is
Yeah, you
that
see what I'm
true?
saying?
Um, yeah, no, it's not the problem. So you got the you use the this is the initial velocity at the time. You can use that time. So I'm just asking you. So you got the the velocity here, then you use that to get delta y, but then you also calculated the time for this top, and that's not given. That was 1.25, but I think you could find it with that information that you have. I'm just
Yeah,
asking,
once
did you do
once
that?
you have the information, you can just subtract it and then set up the unknown variable and then solve for the unknown. Since you have the other ones that you know, you can just set them equal to the to what you're trying to solve, which would be y3. and then it should help you, it should help you get it. So I think that's how I set it up. Yeah, that's how I set it up.
So 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 1 point yeah, I just so that's what you're saying you did. So delta y is 1.2 and t is 0.125. Okay, so 1.2 1 point. What did you say you got? So what did you get for the velocity for V1?
The velocity for V1, I got 4.1165 meters per second. Because we could look at that the 1.2 meters, that given value, we can look at that as y2 minus y1, right? And then the time that it gives us, the 0.125 seconds, we can look
Yes,
at that as t2 minus t1.
correct. Correct.
See what I'm saying? So once we have that, it makes, we just have to add the constant for gravity for our consideration, and then we need to solve for velocity. And then when we set it up that way, it gives us 8.98. Let's see the exact that I got here. So 8.9.
So this is what I'm trying to ask though. Okay, yeah, okay, all right. So all right. So all right, okay. So there's 1.2. So yeah, 1.25 enter square 1.81 times. And then
I get 8.987 meters per second for V1.
yeah.
So
Okay, I get
that's going to be the velocity of the ball when it gets to the top of the window.
right. So I used 9.81, so I got minus 8.986. So yeah. All right. And then you can use that to get within this portion here, you use that to get the
I use that
to
to
get
get,
delta y.
yes, yeah, the change in Y.
And so to get delta y, then it's going to be that squared divided by 2g. Square that thing, so square that, divide 2, and then 9, almost 8.1. So that distance is where you get the 4.11. Yeah?
Yes, the 4
Okay.
point where is it? 1165.
0.11, okay. Yeah. So from there, I guess you could get the total time, which would alleviate having to get this distance here. Did I read this right? In the problem, this is 2 seconds, right? They give the time it takes to fall from the bottom of the window down here. They give that, right?
Uh, Let me see the question again. One point two five top to bottom of the window, distance of 1.2 meters, and falls to the sidewalk. No, it doesn't. Wait, it says assume that the upward flight is the exact reverse of the fall. Time of ball spent below the bottom of the window. That's the time it spends below the bottom of the window.
Yeah, so falling from the bottom of the window to the ground. That's
Yes.
the way I read it. So that is the time then. Wait a minute. Is it the total time or oh,
I think it's the total time. So you divide it by 2 to get 1 second. You take T3 minus T2, and then that would be the 2 seconds divided by 2. So it would be 1 second.
okay, then I screwed up.
Because otherwise you'd end up with double the height of the building.
No, not double the height, just doubling that section,
Or
which
in
I
that
think is
section, yeah.
which
Yeah.
is what I think is what I have. So I screwed up. I think the only thing I did wrong though is that should have been 1 second. I read it as going down and not coming back up. My bad. But I also didn't see. I think we're going to get the same. If I put that in, I think I'll get the same answer. I
Yeah,
think maybe not.
you'll get the height of the building will come out to like 20.43 meters.
Okay. All right. My bad. I'm having a very good week with these problem solving. Um, but it's really interesting though. Still, it's always valid. Let's try to get some value out of this. Or you did. I actually didn't see the way you did it. I didn't see that initially. Remember when I said there's no other way to do the problem? That's not wrong. That's not right. You could do it what you did. I just didn't see that. But doing both of these, you end up getting the same answer. I just had the wrong value in there. So I apologize. So yeah, it's going to cut this in half. It's going to cut that in half. And that's it's going to cut that in half, and that's the average velocity. Yeah. And if you take, because yeah,
So we take that and then we add or we take the 0.125, the distance from the top to the bottom of the window. So that'll give us the remaining distance, because that's the 0.125. So we take the 1 second, or the 2 second, that given figure, we divide it by 2, that gives us 1. Then we add 0.125, that gives us 1.125.
mm-hmm, yeah,
Right? And then we set it up the same way we found uh the our initial equation, where we take y3, and then we subtract our y1,
yeah.
which is 4.1165, and then we set that equal to our V1, which is 8.98. Let's just call it 8.98, and then we multiply that by the time, which is 1.125, and then plus half times 9.81 times 1.125 seconds squared. And then that'll give us our Y3, which is 20.443.
What are you calling Y3?
Y3 is gonna be H, the total height of the building.
Right. Okay.
Yeah, because for the time, we added the what is it, the point 125 seconds, and then that distance that we have here, the 1 second. So we added both of those,
Mhm.
right? And then we had uh yeah, so we use that for our time, and then we solve the equation out that way for y3, and then that'll give us 20.4.
All right. I'm sorry, what did you get for the final velocity for this? Was it 8 point something here?
uh it was 8 point, what was it, 8.1165.
Yeah, I think that is what you did is a valid way of getting that velocity using the position equation here, and it's this solution. This is actually going to be a negative number here because it's final minus initial. And so that's the negative, that's going to be equal to negative 2.1. And I took that over, so that's plus, you know, plus 1/2 times 9.81 times the 0.125 quantity squared, and then all that divided by 0.125. And I think that gets the velocity that you just mentioned. So do it again. 0.125 into squared 9.81 times 2.1. Actually, it's 1.2. Sorry.
Yeah, it would be 1.2, not 2.1. Yeah.
I was off with sig that time, but so, yeah, 8.9868 using 9.81. It's minus because it'll come out minus, and it is minus because it's going down. So just that B1 speed is 8.986. So that 8. Then you can use that in the position equation, or the velocity squared equation. So that velocity squared in this section, right? Because the initial velocity is 0. So V1 is equal to V1 naught squared minus 2 G delta Y1. That's 0. So then delta Y1 is equal to V1 squared divided by 2G. And so that gives that quantity squared.
Yeah, that'll be our 8.986
delta Y1, yes, so equals, well, not 8, or times 2, is that it? Or divide?
no, it'll be over 2. You said it correctly. It will be 2 times 9.81 meters per second squared.
Okay, so yeah, so that distance, yes, 4.11, whatever. So actually 1, 2, so 4 and 7.
So then now that we have that information, the last bit of it is we take T3 minus T2, or the change in the time, which is the 2 seconds that's given. And we know that if it says the total time spent below and the velocity is constant, it'll just be that time divided by 2, because it's the same speed going down, same speed going up. So that gives us 1 second for our T3 minus T2. And We take the 1 second, we add the 0.125, and that gives
Hold
us,
on, back up. So it says the total time below the window is 2 seconds.
yeah, it says the total time below. So that I assume that meant going down and then back up.
So when you say, when I read, well, I misinterpreted it initially, but also when you just said that, I'm assuming when it says below the window, once it passes the window.
Yeah, the total time is spent below the window. So it
Right.
passes, yeah, it passes that the bottom of the window. It goes in a downward direction. It bounces off the floor and then
Yeah.
goes back up. So the total time it spends below that window is 2 seconds.
Okay. So if one trip going down, going through, that time would be 1 second.
Yes,
Yeah. So the time it takes to get from the top of the window to the ground is 1 second plus 0.125 seconds.
correct.
Interpreting that correctly? Okay.
Yes.
All right. So for this section, then we've got velocity at this point. We got the distance. We could just get the one way to do it, I guess, with this going this route is to get the time here. We could get that time. And once
Yeah,
we
there's
have,
probably a couple of ways we could solve it from here. The way I did it though was take y3. We'll solve for y3. So y3 subtract y1, uh, uh, take our velocity, multiply it by t3 minus t1. So I guess I could give you the numbers that might make it easier.
no,
Uh,
I'd rather just tell me what you're doing, what equations you're doing. You don't have to put them. I mean, so once you had that, you said you got this distance right here.
it's the same equation that we used initially to find the um
Well, you just got the, yeah, I got you. So you took that as the initial velocity to fall through this total distance.
yes,
Yeah. And then that will give you and you know the total time now is 1.125
125,
seconds.
right.
And then you solve for that delta y and then subtracted this distance from
Correct.
that. And that's
Yes.
this guy.
Yeah.
Technically, actually, you didn't even have to do that, I guess. You could just add 4.11 to that, and then you got the whole thing, which is what it's asking you for. And that's what you
Yeah.
did?
Uh
All right.
yeah. And then that gave me 20.43.
All right. So let me let's do that thing. What did we say about this guy? So yeah, time. Okay, so recall that guy. Okay. 1.125 times. Yes. And then 0.125 squared 9.81 times divided by
So I just did y3 is equal to 4.1165 plus our velocity, which is the 8.987 meters per second, multiplied by our time, which is the 1.125 plus half times 9.81 times the time, which is 1.125, and then that's time squared. And then when you input that in, it should give you the answer.
Yeah. So you got 16.4 meters between sections 2 and 3. That's what I got. I'm assuming, is that what you got? Store 6. And then I guess I could find, so dividing 1.2, 2 minus gives this to be 15.11. So adding all that up, we get 15.11, 1.2 plus, and then we call this guy 411. Yeah,
I didn't
20.4.
separate it like that, but yeah, that works too.
Yeah, I guess I just I didn't see that you could do it that way. So I didn't see that. Hmm. All right. Hmm. Hmm. Um, Also the average velocity between those points is four left to find the time, so that position. Um, basically that velocity divided by 1.1. This time is like
I didn't solve for that T1 because it didn't seem relative to the question.
yeah, you don't need it to do you know what your method is quite valid in, but I want to check. I'm checking to see if basically that other way that I did it, if that's actually accurate, if you could do it and get the same answer. So what I want to do, for example, is figure out now that you have that total time, you can figure out what the final velocity is right here, just by using that time, total time, and actually that's all you need. So that velocity would be given that we start from rest. So, that time in the 1.25 or 0.125. So basically times 9.81.
Well, it would be the difference between the two, right? Because if you were to T2 is the distance from the top of the building to the
Mhm.
bottom of the window. Right? So
Yeah,
if you
right.
that's the total distance. So if you added the time that you put there, the 0.9 for T1, I don't think it would give you the right answer.
I mean, it's going to give me the answer. It's not. It's just. I think we're talking about two different things. I'm just simply saying that I used that information that you calculated to get this time, and
Uh-huh.
so within, if you put these two regions together, you can use V equals V naught minus GT, guess 1 plus T2, right? That's going to give you this basically V2,
Yeah,
or
but
this
you see what to do it that way though, you would have to take your T2 would be different because your T2 in this case is the time that it took to go that 4.11 meters plus the 1.2 meters. So it's 5.31 meters is the time to go from the top to the bottom of the window. That time is 0.125. So you would have to your you would have to subtract the value of T1 and then put your T2 separate. Right now your T2 includes the 4.11 meters and the 1.2 meters. You see what I'm saying?
Let me interpret because I think that might be a misinterpretation on my part. Are you saying that you're saying this 0.125 seconds is the time for all of to fall through all of that?
Uh, right? Is that how is that?
That's not how I interpreted it. I might be wrong, but I hadn't. That's why I put it here. I interpreted the 0.125 seconds to just be that distance, the time that it takes to fall
Yeah,
through
no,
that
yeah, because
distance.
it says it says 0.125 seconds to fall from the top to the bottom of the window.
Yeah. So then in that case, I don't see any problem with what I'm doing here. I'm saying that if I put those two distances, I'm not, and I don't really even need the distance. I just know this the initial velocity here is 0 because he dropped it. This is at the top of the building, not the window. And this is whatever the velocity I'm trying to find. But now I have the total time that it takes to do that. So I think I can find the velocity there. I just have to add these two times for this guy, which is what I did. I think you can do that. I know it's not asking for that. I'm just trying to check to see this other way that I did that, if that's correct. When I do this, I get that the velocity at that point is 10.21 meters per second. So basically at the top of the window is going 8.986, and then at V2 at position 2 here, because this is basically, you know, position 0. So it's just, so position 1, position 2, and down here is position 3, and then this is position 0. So at position 1, it's that velocity. I'm saying at position 2, it's going to be 10.21, whatever, meters per second. I'm going to store that. Because what I wanted to check to see if, I think I made a huge error, maybe in that point that I was making, because now you can find the average velocity between those 2 points. So we know that the average velocity between this is going to be, it's like 4 point something. It's half of that, right? It's 0 plus that velocity divided by the total time. And let's see. So that's average acceleration, but the average velocity is just going to be 0 plus v1 divided by 2. So just that divided by 2. And that's like 4.49 something. So the average velocity between these 2 points is going to be the sum of those divided by 2, and that's clearly not the same. So recall 8, recall 1 minus 1 plus 2 divided by, that's 9.6. So that is doing that does give me the average velocity that I had here, 9.6. But yeah, I just screwed that up really badly, because the velocity increases, the average velocity is not the same in each region. The average velocity increases in each region, just like the velocity increases. It's kind of stupid for me to say that. So no, I just screwed up. That the way that I did it is not going to give you the same answers that you have, and I do agree that the way you're doing it is a correct way to do that.
Well, I think it could. It's just you'd have to consider that the T2, the 0.125 seconds is the time that it takes to go 5.31 meters. And then you can separate T2, because like the point on the top, the very top, right, to where it goes to the bottom of the window is that's the time, that's the 0.125 seconds. So when you add the 0.9161 here, that's you're adding something else to that's extra time that you're adding. You see what I'm saying? Because T2 goes from the top of the building to the bottom of the windowsill, which includes the 4.11 meters and the 1.2 meters.
Okay, so that's what I was just asking you, which I thought we were clear on that. Like I interpreted the problem differently. That the 0.125 is not the time from the top of the building to that position, but rather the time it takes to go from the top of the window to the bottom of the window.
No.
In which case,
it's from the top of the question says is it takes 0.125 seconds to fall from the top. Oh, yeah, it does say the top to the bottom of the window. Yeah, you're right. Top to the bottom of the window, distance of 120. Also sidewalk. Okay. So you took the 1.2, and then, yeah, why doesn't that work? That should work, right?
I mean, it were. I mean, I never calculated this value before. I think it actually is giving me the right value because what happens is I think that is right because that's not what I was doing earlier. I still messed up and got it wrong. I'm just saying that it validates that this is the average velocity for that section because this way I calculated the average velocity with the physics equation delta x over delta t because they gave us that information. It gives us 9.6. But now with what you did, we could kind of work around and find other information. And one of those I just wanted to check. So I'm checking that you found this velocity here. Now I can use that information like you did. You found that distance, but we could also get that time. Now that we have that time, I can put all that together and just figure out what the velocity is right there. If I do that, then use the math equation, this guy, to get the average velocity between those 2 points, it should be the same as what I calculated here. And when I do that, 10.21 plus 8.986, whatever that is, 18, 19 something, then divide by 2, it gives me exactly 9.6. So it's a different way of doing. So it validates that what you've done is actually right. It also actually embarrassingly kind of implies that what I did was fundamentally wrong. Even though it's not just the fact that I misread that. It's actually that I think, right? I don't like, is that because I'm not, I mean, that is, so this is correct. So that part I did do correctly, and we did get, so it's also it's matching up with this, right? You can do it yourself. Add that, put that together, and divide by 2. So you're getting the same average velocity from a different point of view. I always like to do things like that because getting the same answer from different points of view validates that it's the right way to do it. But what I said was one of the things I said was that I didn't use that, like the average velocity. I thought it would be the same. Like, that's really bad. Is it not the same in every section? I guess it's not. It's not because the velocity is increasing. So,
Yeah, it's being accelerated by gravity, so you'd have to factor the velocity would be different if you were to separate the two.
yeah, that's a bad error. What I was thinking is that I guess I was thinking linearly, right? Because right, but what can also compensate is that it's going through a shorter distance in the same amount of time. But the relationship is not linear, it's squared because it's that position equation, right? That's what so it's delta y is equal to v naught t plus the 1/2 gt squared. So it's a parabolic function, not a linear function. Although the velocity is linear in time, but the position is parabolic. Yeah, I guess that. But if I had seen the way that you had done it, I would have done that. I would have went that route. I just didn't see it when I laid the equations out. For some reason, I didn't see that you could get that position there but you can using what you did. So that is the one other thing you can calculate from the initial conditions, in addition to the average velocity in this section. Yeah, but I did some quick calculations, and I'm not getting the same, using that. As you can clearly see that the average velocity in this section now is 4 point something. It's not going to be the 9.6, and I use that to get the other thing. So yeah, right now I'm not seeing that was a valid way to go. I'm not seeing that.
I think we would need to use the velocity squared equation again, maybe
To do what?
for the time that we have for the 4.1. There's got to be a way to do it this way too. I don't understand why it wouldn't work. It's just we need a we need another equation, I think, to because we have the velocity here, 4.11. I don't know.
Yeah. I think this the way you did it might be I mean, once you get that, you can go a couple different routes, but that's the first thing to do is to get once you get that, then you can go to other with validity, you can go to the other sections, namely the first section there, and get that other information. I don't think that this was right here. Getting that average velocity and then using it over here in section 3, because now, well, I mean, I know the average velocity is going to be different. You could do the same thing. You can get the final velocity it takes to fall through here, right? And then now that I have this velocity, calculate that average velocity. I can already see it's not going to be, this is 10, and this clearly the velocity is going to be larger than 10 here. So already I can see the average velocity in this section is going to be larger than 9.6, because the average velocity will just be that number plus that number divided by 2. And that's what I had said over here when I used that. It's bad. But I didn't see any other way at the time. I thought that was one way to go through. Yeah. All right. Well done. Good job.
Thank you.
And yeah, Kareem, it is multiple choice questions. Just multiple. Like I think I answered that already. Yeah. All right. Yeah. Yeah. Cool. All right. Well, that's somewhat humbling, but I think that's it. I think that's how to do it. So, if you want to hang out, I can do a few more problems. Anything that you've been working on, any other ones, that you had some difficulty with. I guess we spent all class doing problems today as well. But I mean, we're preparing for a test, so it's not that so off. I apologize. I do have prepared problems. I was just picking some ones and supposed to doing some of the ones I've done before. And I probably should have looked at them just so I could do it faster and not waste time to do it more efficiently. But it's a pretty good problem. It's a pretty rigorous problem. Like go through a lot of different things. I think we beat it to death at this point. But do you have any other questions or problems that you've seen that you would like me to take a look at or want to do in class? Anyone?
No, I don't think so.
All right. Well, I'm going to let you go. I'll be updating the stuff. You can look for that. We'll still, I'll put it out. You have plenty of time. And I know I'm still answering some emails. A bunch of emails came in the past day and a half. So I have to see if, some of you needed some more time for homework and that stuff. I'll give you that. Just
Professor,
keep
the
working.
lab
Yeah.
2 that's due today. I'm sorry. Lab
Yeah.
2 is due today.
I thought I set it up for Thursday or Friday. It's a little bit short because I just put it out. So if that's the case, I'll give you more time. This wait a minute, lab 2, maybe it was. I don't know. I might be mixing classes. Well, you need more time.
Yeah, I haven't started it yet. I didn't know it was because I remember there was a thing where it was gonna open and close on the same day. So there was something like that that happened, and then
Yeah, I might have
uh,
switched it that day to the 20th. I don't know. Like we can look at it right now. Actually, I can change it if
yeah, it
that's
says due September 20th.
so.
Professor.
Yeah,
So the test is gonna be open this Friday.
yeah,
Okay, and it's gonna be throughout the weekend. It's gonna be due on Monday night, correct?
yes,
All right, sounds great.
cool. Yeah, well, it's not in class.
Yeah, it says today.
I'm trying to get it out of the way this week. I'll give a couple more.
Thank you, Professor. I really appreciate
Yeah,
that.
no worries. Yeah, I just didn't want you working on that on the weekend. I want you to finish it before the week so you can focus on the test and study. And that's why I just, but whatever. We did miss some dates there early on, so whatever. That's all important. All right. Anything else?
No, thank you, sir, and I appreciate that consideration.
Yeah, no worries. All right. Well, if that's good, class dismissed. And yeah, I will have a good weekend. Be safe. All right.
Thank you, Professor. Have a good weekend.
All right. You too.
Thank you. Have a good weekend, Professor.
Thank you. Have a good one.